Hey everyone, welcome to my presentation. My name is Prajith Prasad and I work as an associate software engineer at Red Hat. I joined Red Hat 1 year back and I joined as an intern. I got converted to full-time employee around February of this year. So to talk a bit about myself, I love to code, I love to automate, and I love creating different kinds of applications, and I do a lot of projects. Non-technically speaking, I watch a lot of films. I love to travel, and I read quite a few books. And yeah, so before I start my presentation, I'd like to take a moment to thank the organizers of this event because it wouldn't have been easy, given the current situations that our world is facing. So I'd like to thank them. And yeah, so let's start the presentation. So today the topic on which I'm going to talk about is blockchain enabled decentralized storage cluster. So I believe that the subtitle which I've added there has caught your attention. So basically what I'm trying to say is, just to quote it again, what if I say the most secure way to keep your gold is to keep it in a place where it's accessible for everyone? The main intention behind that quote was to subtly hint, about the psychology behind all such systems, that is accountability and prevention. Let's say that you're keeping your gold, apart from a vault. You've decided that you keep your gold in front of everyone. Let's say that in a public place, and then you decide, okay, you'll keep it in the middle of a public place as a statue or some kind. And so, what are the preventions that you take? You add cameras, and then you think of different kinds of systems which enables or which keeps your gold securely. So that's basically, in a vague way, I could say that that's basically what decentralized storage is, or decentralized system is. So yeah, moving on. So in today's agenda, we'll be discussing about primarily we'll be discussing the difference between centralized, decentralized, and distributed, and then I'll be talking a bit about what decentralized storage is. That is what the scope of this current, talk is. And then why do we need this? And then I'll be moving on to talk a bit about the methodology, and then we'll be ending it with the future scope. So before I start, I'd like to say that Storch, was one of the inspirations. But when I started this, Storch was has a pretty good white paper in which they have mentioned their own way of implementation. So Storch is basically a decentralized storage application. A company that's a startup and it's an open source company, so their code is in GitHub. Although their white paper is very interesting, they have different takes and different kinds of implementation that helps them with other complexities. So yeah, so basically there are three types, major types of distributed systems. So first is centralized systems. So centralized systems are basically a system with a client-server architecture. Basically you request the data and the server, you request the data and the client goes with your request and gets your answer, and that is the response, and from the server, and then client gives it back to you. So maybe I'd say that imagine an application where you request some kind of data from that server, and then server goes, from the client, and that client goes and fetches the data from the server. Let's say maybe I'm not sure if Wikipedia is a good example here, but maybe I could say Wikipedia. You are requesting the data from one of the Wikipedia clients, and the client goes and fetches from the direct server, and then it gives you the response. So that's centralized system. And the next is, I'll explain distributed and then come back to decentralized. And so the next is a distributed, and distributed is very popular kind of system. It's like a system in which the final behavior of the system is, it's basically there is no single entity that receives and responds to the request. It's basically Google search system could actually be a very good example here. Each request is worked upon hundreds of different systems, and which further goes and fetches the data and then returns back with the response. So I would say distributed with a lot of nodes, but with one master kind of thing. It's basically multiple computers working together to accomplish one single task and returns the result to the search query. And this is distributed. Moving on to the decentralized system. This has become popular very recently with the massive hype of Bitcoin and blockchain. And I believe that a lot of current organizations are finding different applications that they could use decentralized systems with. So basically in decentralized system, every node makes its own decision, and the final behavior of a system is the aggregate response of each node. So there is no master and slave. There are everyone is has equal rights. So yeah, so let's say that if there needs to be a decision taken, it's a collective response. So it's truly a democratic way. So this is decentralized systems. So these are the three major systems which I wanted to discuss here, because there has always been confusion between decentralized and distributed. So even myself, when I was in college, I kind of pondered upon what's the actual difference between decentralized and distributed, because not every distributed system is decentralized. So what is decentralized storage? So here, the scope of this title, this slide is to give you an overall understanding of how a decentralized peer-to-peer storage network works in an overall way. Kindly note that this is from my perception, and a lot of companies could alter it, and they could have their own strategy. But I believe, like, overall, this is the way almost all the decentralized storage systems are going forward. So let's say that myself, I'm having a data in my hand. Let's say that I have a photo or a video or a text, whatever. And let's say there is a decentralized system with 10 nodes, including me. So that's 9 other nodes and 1 mine. So in a decentralized system of 10 nodes, and I'm connected in it, and I decide that, okay, I need to, send this data to the cloud. And so I take the photo and I upload it in a web UI or in a folder, no matter. And then what happens is it gets encrypted, right? And then it gets sharded or erasure coded, and then sharded, and then it is distributed among the other nodes. So the distributions can happen at any way. So basically, I'd be having a distributed hash table from my node, and there are different algorithms like Adindia. So basically, it will, it would take with the ability of the data and what are the other variables, it will make a decision on which would be the appropriate node or a computer that is suitable for this particular data. Basically, after all this, it will go and in the end of the day, it will reside in one of the nodes. So let's say that my document, I decide to upload it, and I uploaded it, and it gets sharded, encrypted, sharded, and it's now in 4 parts, and it gets stored into random computers in the network. So now if I wanna, so it provides a secured way, because the other nodes, when they see there's some file downloaded, they wouldn't be able to actually go and read it, because they just have a tiny chunk of a data that too is encrypted. So they wouldn't really, they won't be able to do anything with it, and they can't even erase or decode anything, because they wouldn't be having access to that particular data. So they pretty much wouldn't be able to alter it or do any type of attack in order to fetch the other files which shares the same checksum. So that's not possible. So this is how the storage data is uploaded. And now when I want to download the data, I simply initiate a download request, and it goes. It has a hashing table of where all the nodes or all the data are stored in which nodes. So it will basically go and fetch it and then restructure it, and then gets me back my file. So this is basically an overall architecture on how decentralized storage works. So I'll be explaining each part of it. Let's say, like, if you go on to the other methodologies, I'll be moving on in the other slides. I'll be explaining on how each part can be implemented, like encryption and then sharding, and then peer-to-peer network, etc. So moving on. And yeah, why do we need this? So apart from the usual, the dialogues and the articles and the other things that you might have heard about privacy and the other things, I'd be focusing mainly on the other points here, because obviously those points are already, obviously those are better ways on why we need a entire, or an actual democratic system. But apart from that, I'd say that there is a minimal number of performance bottlenecks occurring, because it's like a big chunk of task, that's evenly loaded. So there is no really a place for having bottleneck issues, and it's high availability is an assurance, because let's say that if I'm a working guy and with the rate of how almost everyone has internet, some nodes are like online 24/7, right? So and also let's say that if I'm having with this, in current situation, let's say that if I'm in a company, or if I'm startup, and which I have, let's say that I'm in a situation where I need to be online 24/7, but I'm having free disks that I'm not using, then this could be a way. I could simply connect into the network, and then I'd be getting money or the other things. So it's high availability is an assurance, because almost everyone, like I just said, might be online 24/7, and more autonomy and control over resources, because as each node controls its own behavior, it has better autonomy, leading to more control over resources. So that's another point. And coming to data apocalypse or data again, this presentation wouldn't be complete without referencing this hit series, Silicon Valley. For those of you who don't know, Silicon Valley is a hit series that that kind of shares the same idea of a decentralized storage. So I that's a simple image from the series. So Datageddon, Datageddon, what it means is basically running out of, reaching a point where data cannot be stored. All the other companies, they could eventually get into a point where the data is, no more could it be accumulated. But I believe we are still years from it. Obviously, that could be a possibility of that happening, but I believe that's not gonna happen anytime soon. But yeah. And the other point is costs of data overhead would always be a problem, because let's say that if I want to create a simple applications or anything, then I'd be forced to rely upon other third-party paid services for them to host my data or my service or my product or whatever. So that's definitely a big concern, because with the costs of raising costs of the data increasing or their services increasing, that's definitely a problem. Especially if the point one of data apocalypse, if that's bound to happen, then obviously the cost of data could also be increased. But yeah, so even though if it's not actually increased, I'd still be if such a system comes into an existence. I'm sorry, such a system exists, but if this becomes very popular, then I'd say that people would much more prefer to host their systems free, or at least without giving them such big money. So Web 3.0, that actually could be a real thing. It is, because I believe Web 3.0 kind of executes the mission and vision that was set by web or the actual internet when it was actually created. So that could, that's actually a very good, very good reason why we need a decentralized storage, because once Web 3.0, a completely decentralized internet is, if that's possible and if that's achieved, then I believe this decentralized storage or pretty much any applications in a decentralized system could benefit us in a long term and a long way. So methodologies. So here I'm going to be explaining each part or each entity like I mentioned above in the previous slides. So for example, I'd be explaining in a continuous way so that it's easy to follow. For example, let's say that I'm now uploading a file. So the first point is file encryption, and then erasure coding, then peer-to-peer. So I'd be explaining it in the same order. So there are 5 points here, but in the middle I'd be explaining a few concepts from blockchain, just so that we can compare, or not just compare, just so that we'd understand the system even more. So the first is file encryption. So the moment we hear encryption, I believe for some of you, you obviously might have thought of SHA-256. So I'd be talking a bit about how SHA-256 can actually be a big advantage for decentralized systems, because let's say that it shares the same vision on on the same, it basically benefits the vision that is being put forth by decentralized systems and their consensus protocols. So let's say that for every, it's known that every human in the world has the same DNA in their fingerprint, or I'm sorry, has different unique DNA and a unique fingerprint, and so unique fingerprint. So it's like if something, if a person is involved in some kind of criminal activities or whatnot or the other things, then they could find out like who this person is, or obviously fingerprint helps them in finding out who the person is and whatnot. So similarly, SHA-256 shares the same vision. So SHA-256 is basically a unique fingerprint for each type and each document. So let's say that I have a JPEG or whatever file and I do a SHA-256 encoding of it, I'd be getting a 64 hexadigit value of it, a unique identifier for that particular document. So to talk a bit about SHA-256, it's basically an algorithm which allows us to generate a hash value, and it's a number, but it's represented in hexadecimal way, and it's created by the National Security Agency of the United States. So so to continue talking about SHA, so it's basically an algorithm and it's really powerful, and I believe the code of the algorithm is not really a secret anymore, because I think the source code is available online, so maybe you could look into it and try to understand how it works. So SHA stands for Secure Hashing Algorithm, and the important thing here is that this algorithm works for any types of document, and no matter what type the document is. So as an input, you'd be basically giving a document, and as output, it would basically give you a hash value. And not just the type, right? Not just the type. It basically gives you, even if you give around 10 KB of a file or 1 GB of a file, it's going to produce the same 64 hexadecimal value of the hash. And that's pretty great thing. And so no matter the input, the hash is always 64, like I said. And that's like first advantage of a decentralized system or vision. So so also it doesn't not just the type of the document. It basically no matter what the size of the document that you give as an input, let's say that you give a 10 KB of a file or 1 GB of a file, and it's just going to produce the same it's just going to produce a 64 hexadecimal characters hash value. And and this pretty much this kind of, no matter the input, the hash is only 64 hexadecimal character. This kind of thing is a big advantage for any decentralized system, because it's cryptographically it satisfies the first rule, not the first rule, it satisfies the one of the rules of decentralized system. And another important point is it's pretty deterministic. It's like, let's say that I give a file with a content, and I get a hash, and if I manage to replicate the document and put in the same input, I'll be getting the same hash. So it's pretty straightforward. And the other thing is it's unpredictable, right? Let's say that I give a hello world and I try to hash it, and I'm getting a 64 hexadecimal character hash, and I just make even a tiny bit change of adding a dot here or there, I'll be getting an entirely different hash. So it's pretty, I won't be able to brute force by plus or minus or anything. It's pretty much fast computation for mining, so it doesn't take a lot of time, and you could just in a snap of a second you're probably getting the hash value. And the next of sharding, it's erasure coding. So basically what erasure coding is, it's in a simple way, it's basically a way in which if your file is split into 3 and you lost around 1 file, you'll still be able to get all the contents of the other file with just 1 or 2 nodes. So it's basically how we decode it or encode it in the first place. So that's erasure encoding. So there are different types of erasure encoding, different types of algorithms that use erasure encoding, but I'd like to simply give you an example so that you can understand how erasure encoding works. So here you can see an example, like let's say that you take a file of size 200 MB, then you split it into two chunks, and each of them has the same size. That is, you split a 200 MB file into two, so you get 100 MB file each. So now you're basically applying a function of n of k on these k chunks to get n chunks. So basically, let's say that if you need 4 chunks, then you would probably be getting 400 MB file. So the file just gets expanded at twice the initial size. So it was 200 MB, but the moment you apply the function, it's now 400 MB. I'll be explaining why it's 400 MB right now. And now the effective way is, like I just said, it just expanded into 2 times. And now if you with just one chunk of the data, you'll be able to get all the other data. So let's say that you split, there's a file, it's in a file of 10 MB, and if I'm applying 4 into 2 function, that actually can be changed, and it's split across the node. I just need one chunk of a file to recreate the other, and I believe like that's pretty cool. Even though the file size is increasing twice, it's still be giving us the security that we need. So even getting into it a bit more, I'd say that let's say a file A here is getting split into 2, and now it's getting encoded, and now we have 4 chunks of the data, right? So let's take an example here. So this is A1, right? A1 chunk of file will be actually having one part of the file, A2 will be having the other part, A3 and A4 would be having some equations by which if we get at least one part of the file, we could probably compute it and get the values of the other 2, and thus get the actual thus we'll be getting the actual data. So let's take a small example. So here, consider that the original value of the object or the data is 95, right? So here what we're going to do is we're dividing the 95 in such a way that x equals 9 and y equals 5. And the encoding process will create a series of equations. So the equations could be x plus y, and then x minus y, 2x plus y, or x plus 2y, whatever, right? And all these number of equations would be based upon the input that you give. So if it's 4, then it's gonna operate in such a way. So it's basically that. So here, once all these equations is calculated, and then you split it across the node, and then you are only able to get 2. Let's say that you are able to get x plus 5 equal to 14 and x minus 4 equal to x minus y equal to 4. Then you pretty much would be able to calculate the the values of x and y with just that. So you wouldn't be requiring 2x plus y or anything. So you can basically recreate your data from your part and then be done with it. So this in a nutshell is what erasure encoding is. I believe there are like lots of erasure algorithms that you could just look up to and see how that works. It's pretty interesting. So let's move on. So an immutable ledger, I'd say that let's again go into an example of what this immutable ledger is. So by immutable ledger, blockchain claims that no data can be altered, or no one can mess with the data, or no one can restructure it, hack, whatever. It claims that it's unhackable or stuff like that. So let's see how that actually is achieved. So let's say that let's take an example of a naive example with a central server. So let's say that I'm planning to buy a car, right? So I go into the showroom, I pay them, and I get the car, and I go with the documents to a government just so that I can, in this example, and then I tell them that okay, I paid this much, and now this particular car with this number plate is mine. And so that guy who takes down has taken the note that okay, you have paid this much, and then you have bought a car of so and so record, and he has created a neatly structured record, and he is putting it in his DB. So now you own the car. But what if that person who writes a record has made a mistake, or since no one is there to verify what he has done, let's say that he has intentionally or unintentionally has made a mistake, and then when he put it in his system, it exposed a threat or a vulnerability, which later on somehow, let's say that eventually let's say that he messed up the name, right? And now technically speaking, I don't own that car, someone else does. So that's vulnerability. So that's like, okay, now technically that's that cannot be happening, because there goes our security and everything, because technically now I don't have the car, so now I'll have to go and register a complaint and whatnot. So now let's see the same exact example if we implement it in blockchain. Let's see how that's going to operate. So in a ledger of a blockchain, the moment I buy a car, let's say through some smart contracts. So smart contracts, I'm not going to go and talk about what smart contracts is, but it's basically, let's say that, okay, there's some kind of an automated record without no human intervention help. So the moment I buy a car, it's been registered, and now, let's say that okay, I'll explain it with an example. So there are 10 nodes. So I go in a network, and I buy a car. The moment I buy a car and I pay them, a neatly structured timestamp data is now, registered in one node. So whichever place which I buy, which I have bought the car from, think of that as one of the nodes in the network. And the moment I buy a car from them, that particular node has now released a data stating that, okay, so and so person has bought so and so car. So now this travels across the block, right? So it is verified, and I will just see how mining works. So mining is a process of verification of whether this is actually the good data, and it's not some other kind of thing. So eventually, once everything is in place, all the nodes agrees that this is good data, and they add it in their own copy of data. So here, let's say that somehow the guy finds a way, the attacker finds a way and changes the node, right? Changes the node in one of the system. So now what happens is, if that change, if it has to be aggregated across this network, then he probably have to, since it's cryptographically linked, he probably have to change the entire block in that particular, entire chain of blocks in that particular node. Because the moment he changes something here, something there, that means that the entire block afterwards is now null. Yeah, it doesn't really matter. That's garbage data. So that sends out, an alert. So that alert part and all is how we implement our system. So I'd like to think of it as an alert. And then, once that is done, let's say that if that's, if that change, once that change triggers some kind of notifications or an alert, it basically would let the other nodes know, okay, that node is corrupted, because it's cryptographically changed. Now, let's say that he has managed to entirely change the data or entirely change the block, making, he mines each block, or he has somehow maliciously figured out a way, which is super hard, by the way, and he has completely, replaced an entire chain of blocks in one of the node. But he has just managed to change one of, the entire block in one of the nodes. So it still hasn't been agreed upon by the 90% of the blocks, because they have another, their copies is different. So, all such systems build up the security so that people can't actually mess up with it. So this is one of the example which I'd like to say on why blockchain is called or known as an immutable ledger. So in cryptography, right, a hash tree or a Merkle tree is basically in which every leaf node is labeled with a cryptographic hash of a data block, and every non-leaf node is the cryptographic hash tables of their child nodes. So let's say that in this example, you can see there are 4 data blocks: L1, L2, L3, and L4. And those, and if you see the first leaf node, it's basically a cryptographic hash of data block L1. So hash 00, that is the leaf node, is basically a cryptographic hash of data block L1. Similarly, hash 01 is cryptographic hash of data block L2. Hash 10, L3, and hash 11 is a cryptographic hash of data of L4, right? So now, once I have been able to compute the hashes of data block, all the other, since I've covered the leaf nodes, the non-leaf nodes, what they do is they compute the hashes of their child nodes. So hash 0 is basically the cryptographic hash of hash 00 and hash 01, and hash 1 is basically a cryptographic hash of hash 10 and hash 11. And it would go again and again recursively until it reaches one hash where it covers the hashes of its child, and we get an actual hash, master hash or root hash, if you will. So this is what Merkle tree is. So coming back into proof of storage. So before I tell you how Merkle tree is being used in proof of storage, I'd like to add that it's up to us, right? Once we figure out the basic implementation of basic necessities of how we need to create a decentralized system, it's entirely up to us on how to create it and how to implement it. So let's say that if I want to go on in a naive approach, then I could probably implement a listener or some kind of thing or an audit track where it goes around a peer-to-peer request response kind of type of thing, to check whether the data still exists here and there across the network. So every client could initialize such a thing. But obviously this would have a lot of overhead, unnecessary overhead. But I just wanted to say that as an example because it's entirely up to you. So if you're able to develop a very good algorithm that doesn't necessarily beats it or that doesn't necessarily follows the architecture but still works for you, then you can of course proceed with that. So speaking of that, I'd like to explain how the proof of storage has been implemented in storage. Right, storage basically has an alternative way. It has two ways, but this is an alternative way of how they verify whether a particular node has a data with them. So the alternate methods is basically what it does is it basically presents a hash challenge, and that hash challenge has to be solved, or it has to be fulfilled in order to accept that data is pretty much there, and it shouldn't take a lot of my time because this is not this is something without any brute force approach or anything. This is not mining completely. This is like a verification method, right? So coming into the actual application of how they have implemented, let's say that so if you see here in this tree, they have created if you can see a root seed there, that's basically client creating a series of seeds deterministically from the root seed, right? So what is seed? Seeds are pretty much basically data that you upload once you download. So let's say that you download a file from the peer-to-peer network. The moment it's downloaded, you start uploading it. So that's called as seeding. And the opposite of seeding is leeching. That's when you keep downloading, but you don't upload. So that's actually a threat to a decentralized system. But that's what seeding and leeching means. So coming back here, the client has created a root seed, right? And then he has created a series of seeds from the root seed. And what the series of root does is after it creates a series of seeds, it would be added to a file and it would be hashed to generate a unique hash answer. So once it's a unique hash answer. So once this client generates the hash challenges, it builds a Merkle tree like the one we just saw before, and it inserts the Merkle root into the blockchain. So and then it publishes or gives the Merkle tree minus the leaf nodes to the other nodes, so that they can verify whether this particular node has whether this particular node, because since it won't be having the leaf nodes, and when it so basically it would be giving, once it's hashes and it's added to the blockchain, it would be giving this Merkle tree without the leaf nodes to the other nodes who has my data, because once they accept it and once I am sending in my seed, it can be matched, right? Because they'll be having the Merkle root or Merkle tree without the leaf nodes, and I'll be having one of the seeds. So I can actually, once it reaches their computer or their node, it can calculate, and once calculation succeeds, then that means that that particular node has my data. So that's a pretty good. I hope that's a pretty good way of implementing a proof of storage mechanism with low overhead. I believe I've been able to explain it properly. So again, again, this is just their way of implementation, and if you have a better way, then you can as well. So this is concluding the proof of storage. Ultimately, this is the proof of storage is our last method, because we have covered uploading of a file, and then sharding, and then we have covered peers of peer-to-peer. Then we saw how strong the ledger is, and how blockchain how blockchain basically made the ledger strong. And then we also saw the proof of storage, and also we also saw the traditional mining. So concluding the proof of storage, the steps of which is basically steps to upload and retrieve a file to and from the network, right? So we split the file into pieces, add iteration coding, encrypt to generate shards. We transfer the shards to various nodes on the network based on the distribution and the erasure coding schemes. So the paying, right? This is where incentivizing comes in. So paying each node upon the completion of an audit, right? So this is basically we need. So there won't be volunteers around the network in real time who would be basically dedicating their disk to the network, because there need to be some motivation for the users, or basically for the users in the nodes to give their disks to the network. So that's when incentivizing comes in. So talking about a business approach, if I am the one who's using the network, and then if I'm the one who's basically making use of the storage item, that's saying that I have a file that I'm uploading it, then I'll probably be paying each node, whichever node has my chunk of data. So this in general, we have concluded how the implementation part is. But to talk a bit about incentivizing, this is very much required, right? Because economically speaking, this is the first time, I might be wrong here, but that I've seen a computer science problem be solved with the help of economics. So that's a good way, and that is very much required, because if it's not incentivizing, we need to come up with some kind of application that would make the user keen on connecting their disk to the network. So yeah, concluding it, I believe I've covered almost all the topics, and I strongly believe that if we do this right, the solutions could open up to a lot of other factors as well. Social media, I believe there are lots of sample tests of social media in decentralized systems as well, but I really believe it could revolutionize, and it could create an actual democratic system in the internet. So you would actually be owning the data. So that's a pretty cool thing, if you ask me. So yeah, thank you. I guess I'll be taking the questions now.